We saw that the first derivative can help us distinguish local minima from local maxima. What about the second derivative? So let's think about what the effect of concavity will be on a critical point. So suppose we're at a critical point. So remember, for a critical point, we're looking at a spot where the first derivative of a function is 0. So suppose that x equals a is a critical point, so that the derivative of f at a is 0. This means that, right, if here's a along the x-axis, that means that whatever the graph looks like at this point, it has a horizontal tangent line because the derivative is 0, so the slope of the tangent line is 0. Now, suppose that at this spot, the second derivative of our function f, so this is an extremely rough sketch of the graph of f, at this critical point a, suppose that the second derivative of f is positive. Remember, this means that the graph is going to be concave up at this spot. Well, if we're concave up at a spot where the slope of the tangent line is horizontal, the only way this can happen is if the graph is like this. Right? The three things that concave up can look like is this, or this. Right? All three of these are curling upwards as you move to the right. But for the one on the left and the one on the right, there's no spot along these little pieces of graph that has a horizontal tangent line, so it can't look like either of those. It has to look like this one in the middle. Well, if we're in this situation where the slope of the tangent line is 0 at a spot where we're concave up, you can see that this is clearly going to be a local minimum. So at a critical number, if the second derivative is positive, we have a local minimum. Well, let's see what happens if we're at a critical number where the second derivative is negative. You can guess it's going to be the opposite, but let's just make sure that it works. So if we're at a spot where the second derivative is negative, that means the graph is concave down. So if here's our critical number a, so suppose our graph goes through this point. Because we're at a critical number, the tangent line has to have slope 0. And the three possibilities for what the graph could look like when it's concave down are like this, or like this. But again, the one on the left and the one on the right, those don't have a spot on them where the tangent line is horizontal, so those can't be the situation we're in. It must be the one in the middle. So the graph near this critical number a, the graph of f must look like this. But that makes a local maximum. So you can see just by looking at the sign of the second derivative at our critical number, we can distinguish local minimums from local maximums. At least some of the times. The one situation we haven't looked at is what if the second derivative is exactly 0, right? We know what happens if it's bigger than 0 and if it's less than 0, but what if it's equal to 0? Well, if it's equal to 0, the situation is unfortunately substantially more complicated because we've seen that, so if here's our critical number a, and here's a point on the graph of f with a horizontal tangent line, we've seen that there are actually lots of ways for the second derivative of a function to be equal to 0. When the second derivative of a function is equal to 0, that means that you have just at that spot, you have sort of a flat spot in the graph. Just for a moment, the graph is going straight instead of curling upwards or downwards. So it might be sort of like this. Right? So at this spot right in the middle, there's a horizontal tangent line, but because it's also an inflection point, right, at this spot in the graph is switching from concave down over here to concave up over there, concave up. That makes this spot at A an inflection point, and at an inflection point, the second derivative has to be 0. So it's possible, so let's make a list of possibilities for this situation. So one of the possibilities, if the first derivative at a is 0 and the second derivative at a is also 0, it's possible that x equals a is not a min or a max. let's see. So you can see that sort of the inspiration for this particular shape is sort of x cubed. All right. But really, x to any positive integer power bigger than 3 will have a second derivative equal to 0. So what if we had a graph that looked like this? You can see that this graph is sort of looking like x to the 4th. Well, you know, x to the 4th, the first derivative is 4x cubed, and the second derivative is 12x squared. And sure enough, at 0, both of these are 0. So, right, this shape does have a spot right here where the second derivative is 0, and the first derivative is also 0. But you can see that, in contrast to our previous example, this time, this spot in the middle is actually a local min. So it's possible that x equals a is a local minimum. But, you know, there's one more possibility. What if we took this blue shape and just flipped it upside down like this? So it still has a spot right in the middle where the second derivative of this green function is 0, and the first derivative is also 0 at this spot because the tangent line is horizontal. And so this spot in the middle, this time, is a local max. So the green graph shows us that if the first and second derivatives are both 0, it's possible that x equals a is a local maximum. So, you know, there are so many possibilities for the case where the second derivative is 0 that, right, anything could happen. So what this is telling us is that if all we know is that the first derivative is 0 at a and the second derivative is 0 at a, we don't know if this spot on the graph is a local min, a local max, or neither. In other words, knowing if you have a critical number, knowing the second derivative is 0 does not give you any information about whether you have a local minimum or a local maximum. It just doesn't tell you anything at all. So to summarize this situation, this is usually called the second derivative test. If we have a function that has two derivatives, so that's what I mean by twice differentiable, on an interval containing a critical number, so the derivative of f at a is 0, then there are three possibilities. The first is if the second derivative is at that critical number is positive, then that critical number is a local minimum. If the second derivative at that critical number is negative, then that critical number is a local maximum. These look backwards at first, so careful to not get them confused. And then the third possibility is if the second derivative at your critical number is 0, you can't draw any conclusions about whether that critical number is a minimum or a maximum. So notice that we are not saying that if f double prime is 0 at a, then a is neither a local minimum nor a local maximum. That is not at all what we're saying. Remember, any of the three possibilities can happen when the second derivative is 0.